which I read while I was preparing the talk. So if you're interested in this, I'd say start there and work backwards. So here are my conclusions. It's interesting to think about electron analogies with liquid crystal states. It's interesting to think about these liquid crystal states in relation to superconductors. I think this is a very new field of research, and we have STM, but it would be great if we also had other forms of imaging that would help us see what we've got. I strongly suspect, as we're seeing down here, this is the point about the Hamiltonians, let me skip over that since I've just said it. I strongly suspect that we might be being limited by our imagination in the complexity and the richness of the kind of textures that interacting electrons can adopt. And something that heartens me, and maybe is the closing picture I'd like to leave you with, many of you will have played with ferrofluids, right, in magnetic fields. So you can get these, this is a photo of one of the things that a ferrofluid will do when you apply a magnetic field to it. When you think that that's just a fluid of interacting classical particles which have couplings to external fields that you can supply, you know, I think it would be very difficult to convince a condensed matter physicist that anything as complex and beautiful as that was going on in a solid. But then maybe this type of image is the first step to realizing just how rich things can be. Probably things can get richer than that as well. So with that in mind, I think electronic liquid crystal physics is here to stay. I'll stop talking, and thanks for your attention.
Thank you very much for this beautiful review. So the talk is open for questions.
So the minimal models, you say Hubbard model, but you talk also about spin-orbit interaction.
No, beg your pardon. So the Hubbard model is a famous, you know, minimum model for correlated electron physics. These guys are now writing down models with trying to put a J into the model. Right, so it's not just from the Hubbard model to the TJ model. It's a model with a particular structure of T's, and it's particular based sometimes on band structure, and a particular how simple a J can you put in. Now that J is going to include the spin orbit effects in some effective way, right? And what they're trying to see is how simple can the J's be in order to capture the fundamental physics of what's going on. And the interesting point is, apart from getting the orientation of this D form factor density wave wrong, really very simple ones that don't look all that, you know, the Hamiltonian could be written to look not much worse than the TJ Hamiltonian. Several groups have now done, what is it, it's a weak coupling renormalization group analyses of the properties of those Hamiltonians, and all the groups get that you get D-wave superconductivity as the leading superconducting instability, and this D form factor density wave or smectic as the leading particle hole instability. And so I don't think now there's any doubt. That's 4 or 5 groups. They're all referenced in that Sachdev paper. I think all the theorists agree that that is the property of that model. The other thing to say, though, is that in all honesty, experimentally, you see the D form factor density wave just right next door to the superconductivity in the phase diagram. Theoretically, they would say that the superconductor should be way more prevalent, more likely to happen than the density wave. So they don't understand properly the balance between the density wave and the superconductor. I think it's a big advance, though, to be able to be getting this cross-correlation between 2 different states, and now the knowledge that in many systems we see them next door to each other.
More questions for you?
Yeah. So, in your view, what is the relevance of these smectic or pneumatic phases to the pseudogap phase, to the pseudogap physics?
So the density wave is more or less properly established now not to have exactly the same temperature dependence as the temperature dependence of the pseudogap. But it's always happening, you know, below the pseudogap temperature or similar to it depending on the doping. So I think it's perfectly possible. Whereas the nematicity, as it's claimed, if you believe the sort of claims that I showed you about electronic anisotropies, the onset of the electronic anisotropy is pretty close to the onset of the pseudogap. I mean, there's obviously a range, different probes see it in slightly different temperatures. So it's perfectly possible that what you have is a melted D-density wave. as the pseudo gap. I think that's one of the possibilities. I mean, other people, including Steve Kivelson, who I talked to a lot, and who, you know, in some senses revolutionized the liquid crystal. If you asked him at the moment, he would say that the more exciting thing still is that everybody uses the word density wave, but there's no charge density measured associated with that, and so it's some form of real space structure. One of the big competitions is with pair density waves. People wonder whether these are actually crystals of Cooper pairs themselves, of preformed pairs, and it would take careful Josephson tunneling STM or something to sort out what's going on there. But I think it's, you know, one of the big, if you asked Sachdev and the guys from that group, they wouldn't want to listen to anything about a pair density wave. They're pretty convinced that it's a standard density wave of some kind, and that its form factor is really telling us that it's related to the same microscopic physics as the superconductivity, and that probably, I guess he would say, yes, the nematic is when it melts.
Questions or comments? I just have a small question. So Seamus showed us his his recent paper where he tries to make the connection between heavy fermions, pnictides, and cuprates. What about heavy fermions for the nematicity?
So there's some evidence of nematicity in heavy fermions. There's some evidence that uranium, ruthenium-2, silicon-2 has anisotropy in the hidden order state. Experimentally, I'm not aware of other examples, but I'm not totally sure. I'm not totally sure how hard and how carefully people have looked, because this is physics you have to really look for. You can miss it. It could be there. B, you have these theories. So the claim is, and this is, the paper he showed you is one of the papers I was saying with Dong-Hai Lee, where they take this simple Hamiltonian. For them it's enough to say it contains aspects of heavy fermion physics. Given that it says that the superconductivity should be way stronger than a density wave, they probably wouldn't be that surprised that some of the, the fact that they're seeing D-wave superconductivity apparently in some heavy fermions is enough, right? But I don't know, I'm not honestly sure. Of course, if people look for it and don't find it, they probably don't publish that. So unless I don't know the heavy fermion experimental groups well enough to know whether people have carefully looked. We've had plans. I mean, we want to. The other thing is big vector magnets could help you look for it. And so one of the lists that we have is to look for, say, cerium, ruthenium-2, silicon-2 near the metamagnetic transition. Is there any sign of electronic anisotropy there? And that experiment would take about a week, but we haven't found a week to do it, so we should.
Okay, thank you. So then I think we can close the session. Thank you very much, Andy. Thank you.